Yeah, so I just wanted to thank everyone for sticking through a long day and a long week, and also thank Boumediene for organizing such a nice conference. I've been looking forward to it for a while now. So today I'm going to tell you about continuum attention for transformer neural operators. And the motivation from this work was really like using ChatGPT and being impressed with its performance and wondering what the heck is a transformer, digging through a little bit and then finding some interesting things and noticing some connections to scientific ML and moving from there. So I'm hopeful that you guys will learn a little bit about just what a transformer is and what attention is, because probably these are buzzwords that you've heard, but maybe haven't actually seen just kind of how it works. And then, yeah, show some little applications to some operator learning problems in scientific machine learning. So first of all, at a high level, I'll tell you that attention is a building block for transformers, which is the architecture that underpins most of the large language models that we're seeing right now. And this attention mechanism is successful at capturing non-local correlations in sequential data. And there's, in addition, been recent interest in applying these attention mechanisms to operator learning. What is operator learning? We've heard about it a few times during this week. But the idea is that, let's see if I get a, oh, that's fun. Actually, that's overwhelming. The idea is that we may be interested in mappings of functions to functions, but we have to acknowledge that the data arrive discretely and that we have to run computations on computers. So that means that we're doing discrete numerics as well. And so the overarching idea of operator learning is that we want to both respect the discretizations that we have to do and their compatibility with the continuum that we believe is underpinning the problem that we're addressing. And so here we formulate continuum attention, which leads to discretization invariant implementations and allows us to design some efficient transformer neural operators. And so this is work that recently went on the archive, maybe a month ago or a few weeks ago. And so when that happened, I decided to change my topic to this, because I thought this would be fun. So here's the short outline. I'll tell you a little bit about operator learning in general and the formulation, and then specifically get into transformer neural operators and attention, what they are and what they can give us. And if I have some time, I'll tell you about how to make these a little bit more efficient by introducing some patching and some Fourier layers and things like this, and then show you some numerical results comparing performance and cost and efficiency and things like this across a few different methods for a few different test problems. And then I will conclude by stopping talking. So the general idea of supervised operator learning is that I'm interested in some map that's out in the world. This is SciDagger, and it maps a function space of inputs to a function space of outputs. And so the idea is that maybe I get data, capital N pairings of inputs and outputs, and this output is the response of this infinite dimensional operator. And so here the idea is that the data are functions. So in particular, this little in maps some domain, which might be an RQI, to some RDI, right? So it's a Euclidean to Euclidean mapping. And how can we start to address this with neural operators? The idea is that we define some finite dimensional parameter space and some function class that can be parameterized by those parameters and then map function inputs to function outputs. So we want to design class of functions that can do this. And the idea is that there's some function approximation where I can find a particular element in this class of parameters such that my learned parameterized operator is approximating the real one. By the way, please interrupt me because I don't want to lose people for 25 minutes. So if I'm not being clear, just jump on in, and that's all right. So we'll stay on the same page. Some synchronization, some forcing to keep us on the same page here. That's not what I thought was going to appear, but that's fine. So in order to train this neural operator, what do we need to do? We want to define some kind of loss function that tells us what a good parameter is. And what's a good parameter? It's one that minimizes in expectation the difference between the true operator and the one we've learned across inputs and outputs that are distributed according to some data distribution. Of course, in practice, we only get finitely many data elements, so we have capital N of them, and so we empiricalize this expectation and minimize this sum, and that's what I'm writing here. Let's find out what the next slide is. Nope, okay, that's fine. What's that? Yeah. Well, so the thing I was hoping that would pop up on the previous slide is about the relationship between the discrete and the continuum in the context of operator learning. And so if I were to go back here, you'll notice that I'm defining a minimization between this operator's output and data, but the data in principle actually arrive discretely, right? And so this is a little bit dishonest, what I've written here, because I'm pretending that I have this infinite dimensional object and I'm evaluating it on infinite dimensional inputs. And that's a little bit dishonest because what I have to do here is run it on a computer. So there's kind of an intermediate step here, which is discretize. And this is kind of the order that you want to think about things in, where you want to empiricalize and discretize into algorithms and discrete data and then minimize on that. And you want your choice of discretization to be consistent. So if, for example, I gave you a more refined version of the inputs and outputs on some mesh that my operator that I'm learning is still nicely behaved. So this is this idea of discretization invariance. All of these are like principles that have been around for a long time about relating discrete data and continuous ideas via computation and numerical analysis. So here's just a simple example of an operator learning problem that relates to dynamics. It's a smoothing problem. So here I'm looking at the Lorenz 63 system, which is a three-dimensional ODE system. And the idea is the following. If you give me a trajectory of the first coordinate, and for example, the initial conditions of the second two coordinates, can I recover the rest of the second coordinates? And this is a well-posed problem. And so we can seek an operator that does this mapping. And this is a common problem that shows up in like oceanography and other things where you have partial observations of a system, and what you'd like to do is recover the hidden variables of the system. And so here what we do is we simulate a bunch of trajectories and do supervised learning on this. So we show ourselves the first coordinate as input, and then we show ourselves the other two coordinates as output, and we get good at predicting those two hidden states from the first one. And so here's an example of this. So here on the first column is an example of median test error, and this was on the right was our worst case example. The point is that we give ourselves an input function here, which is the first coordinate of the system, and then we're able to predict the y and the z components over time. Yeah, Christian.
In the previous slide, when you say you have measurements corresponding to x and how it traces with respect to time, you have initial conditions of y and z, and you're kind of mapping these two to how y and z trace with respect to time. So implicitly, I am assuming that how x behaves with time is the same push-forward map for y and z. Is that correct?
Well, the idea is that they all evolve together. So that's what this coupled system of ordinary differential equations does. Is that yes. That the idea is that the evolution of x is deeply related to the evolution of y and z. Yeah. Thanks.
And then we don't need to have any assumptions on this relationship.
Well, the idea is that through data, we can uncover a representation of that relationship, if there exists one. And what I'm promising you is that by writing it this way, there does exist a relationship.
So,
yeah.
Is there any underlying assumption there that we have?
Well, the assumption here is that that there is an existence. Yeah.
Thank you.
I mean, there's some deep details that I'm not getting into about what types of operators you can and cannot approximate. And I won't really talk too much about that, but I think that's a very interesting topic. And some folks this week have discussed this actually with like the non-self-adjoint operators. And so there may be some subtle assumptions that I'm not even thinking about that we're making. So here was just an example to get us going. But I want to tell you about transformers. Okay, so what is a transformer? It is an operation psi that maps input functions to output functions. And it's a composition of 3 functions, actually. So if I give it some function u, this could be either a sequence, like text, or perhaps a trajectory, like I just showed you. We input u, we pass it through 3 functions. So t in, then e for encoder, and then t out. So there's some kind of initial lifting, then kind of the heavy work of the transformer, and then some final remapping. So in general, we can think of these t-ins and t-outs as pointwise neural nets applied pointwise on the domain of u. And then this e, this is really the special sauce. It's a map from the lifted space on t-in to the space that t-out is eating that takes the following form. So it takes a function v and runs this attention mechanism, which I'll tell you about. The key thing to notice about attention is that it's a non-local operator on v. And then we add it to that initial v. A lot of times w1 is actually just the identity here. And then we pass this through a neural network, which applies a nonlinearity to the function output here. And then we have another residual v here. And so this is sort of like one layer, so to speak, of the transformer encoder. Sorry? Well, I'll show you exactly what I mean in the next slide. But what non-local means is that if v lives on a domain, a local function on that domain, so implicitly this is, let's say, of x, where x is an element in D. This would be local if I can compute a of v at x using a of v at x, right? So in other words, in a sequence sense, a local operation would only depend on my current element of the sequence, what the new element would be. Whereas non-local would depend on neighbors or anywhere else in the sequence. Exactly, yeah. And so let's get into the details of attention. I'm going to specifically think about discrete domains. So here we have a sequence from 1 to capital N. You could think of this as a sentence or a time series of length n. And what is it going to do? So this operation maps sequence. So first of all, I'll say that it maps sequences of length n mapping into du to the same function space. So it, for example, if I have a 1D time series, it's going to map you to another 1D time series. How does it do this? It has 3 parameters. These are matrices in the discrete time case. So we have q, k, and v. Let's assume those are fixed for now, although we're going to learn them. And so the idea is that if I want to know the attention at domain location j, it's actually just an expectation of this matrix v applied to u at a location k that is distributed according to a special measure. Okay? And the whole bit of attention is defining this measure. So this measure is defined as a softmax. So softmax is basically exponential divided by sum of a bunch of exponentials. So the softmax, this measure is the softmax of an inner product between u at its current j across all of the other locations in the domain. And I say that, but I didn't mention that also we're lifting it, so it's actually a weighted inner product according to these learned q's and k's. Okay? And so this is the attention mechanism that gets applied to sequence data, like words. I didn't explain how words become numbers. I'm kind of skipping that part. Okay? But so this is what gets applied in transformers. And then what's interesting is that I'm going to flash you a very similar slide, but I'm going to call it continuum attention. So now I'm going to say that I just have a new domain D. Instead of writing Dn as an index set, now I'm just saying it's like our Q. And now I'm going to write exactly the same thing, except instead of J, I'm going to write X. X lives in that domain. Now I'm going to write Y instead of K. Y just lives in my domain. And I'm going to write the same exact measure here, except now I have X's and Y's, and these are in a continuous domain. So that's the only difference of what I've written. But now we have an operator that maps between functions and functions. And what's pretty cool is that it turns out that this discretization at a discrete set of points on your domain, as you refine that domain, converges to the operator or the continuum definition. Yeah, Faye.
How do you correspond your discrete U and to continuously to some kind of function mapping?
Yeah, so the idea is, yeah, go ahead. Sorry, yeah, so this A is defined as the integral. So this is the A that gets approximated with this guy. And so the idea would be that, for example, you can look at this integral and you can run let's say a right-Riemann sum on it. And if you decide that your domain points that you're going to do the summation on correspond to the domain points that you get data on, right? Then that's actually what you're running here. So yeah, does that make sense? So the probability is really just the measure. So we're really just weighting. This is just the measure for our integral. So that's why we have a sum. Oh, sorry. So in other words, we're equally weighting each element of the probability. But you could try and do something differently. And actually, this is a great question because I'm not getting into this. But if, for example, you received data that are irregularly sampled, right? So sometimes, let's say yj and yj plus 1 are close together, but yj plus 2 is far, then the way this is written isn't really the optimal way to go. You would end up doing like a trapezoidal integration where you keep track of how far apart these grid points are. But the core idea here is that the discrete attention actually approximates the continuum attention. You can look at this from different perspectives if you want to think about it from Monte Carlo integration or from finite differences. These are all kind of valid ways to understand it. The second theoretical result we have is about universality. And it turns out that our universality result is really a corollary. Oh, yeah. About it.
Question about the discrete attention.
Yeah.
The summation here that you approximate the integration with, do you perform the summation?
Yes. Yes. So in practice, if we want to compute in operator learning, we have to do discretizations. And so the discrete formulation is exactly the right one to do if you have uniform sampling. You can pick a fancier discretization if you want, but the existing discrete attention is like a totally valid discretization of the continuum. Yeah, so these are parameters, so to speak, that define the attention mechanism. So these are lifting matrices. So this is lifting U, and Q and K. You can actually combine Q and K to be one matrix, as you can probably tell from this inner product. But in practice, they find efficiency in representing things this way. Yes, yes. So all of these are parts of the parameters of the system that you're going to learn. Yep. So the second result has to do with universality, and it basically says that that we can approximate functions on Banach spaces, operators that are defined between Banach spaces. And this turns out to be a corollary of Sam Lanthaler's recent work on approximation theory in operator learning. The key idea is that if you have both a non-local operation and a non-linear operation that are composed with each other, that this leads to universality. And so then we just show that we have that structure, and therefore the result holds. Yeah, so this is just that we have a soup norm bounded. Okay, so there are some important practical generalizations. One is that we actually have to include a positional encoding, which means that in the input, we're not just sending the function or the sequence. We also concatenate that with its coordinates, right? So if it's a time domain, then we specify what that time domain is. Another important thing is that we actually compose this E map that I told you about many times with itself. So it's not just one of these layers, it's many of them. There's also this idea called multi-head attention. So I explained one one attention, but actually you run it a bunch of times with different learnable Q, Ks, and Vs, and then you stitch them back together at the end. And then also there's this layer normalization that goes in. So when there was this recursion that I showed you here, this isn't exactly faithful to the implementation. There are layer norms between some of these big parentheses. And this is another like deep learning trick that helps things. Okay, I'm gonna skip this efficient scaling business in the interest of time. The short version is that people realize that this is expensive to run attention on long sequences. And so there's ways to deal with this with patching. And we were able to set up our own patching formulation. So we ended up with a vision transformer neural operator and a Fourier attention neural operator. Doesn't really matter. The ideas are to make it efficient with patching. So what did we see? So here's an example of wow, this really is an old slide. That's too bad. I thought I sent them a new one. So this is the Darcy flow problem. What's that? Okay. So this is the Darcy flow problem, where we have piecewise constant coefficients for the PDE, and we're trying to map to a solution of this PDE. So this is a mapping of coefficients to the spatial solution given.
That's your diffusional data model.
What's that?
Yeah, that's your A.
Exactly. Yeah, I had all these labeled. I don't know. Yeah, that's too bad. So yeah, exactly. So this is our A, and we're trying to learn our U. And so we collect a bunch of them and train on it. And this is the truth. This was the prediction. And this was the errors. So they looked close. Wow, this is a very old. Well, oh well. And then this is the Kolmogorov flow example. So this is 2D Navier-Stokes. And here we are trying to learn a map from some time t to a time t plus delta t. So you have this 2D Navier-Stokes flow. You give me some snapshot of it, and I want to move it forward a bit of time. So we collect a bunch of examples of that, train on this, and then try to run this. So what we see here is the initial condition, and then here's the true perturbation of the initial condition in a data example. So it's close to 0, but it has some interesting structure. And then this was the perturbation to the initial condition that we learned. And so the difference between these two guys is shown here. By the way, the two rows are showing our median performer and our worst performer in the test set. So we also compared a couple different architectures in terms of both their parameter hunger and their computational complexity across these two problems. And the important things to note are, so here on the top are our how parameter hungry things are. And we saw that the Fourier neural operators, which is another kind of method from a few years ago, had much higher error per parameters than some of our approaches. But if you look at complexity, we realize that these attention neural operators are very expensive to run. And so that's where we're actually paying some of our price. I think maybe the core understanding is that if you're willing to spend a lot of computational time, you can go beyond the performance of these FNOs. So with that, I'll just wrap up and say that, so for one thing, we found that Monte Carlo approximation theorem relating continuum and discrete attention, universal approximation theory for the neural operators. We did a bit of patching and found that they're a reasonable approach to do operator learning. There's some more work needed to deal with attention and, the cost and the accuracies. So I'll show you some references. And yeah, I wanted to thank you guys again for your attention. It's a very special thanks to Edo, Nicola, and Andrew, who worked on this paper with me. And yeah, I'm happy to take questions.